What if I told you the metal holding a fighter jet together, replacing a shattered hip, and wrapped around your wrist in a luxury watch, started out as ordinary-looking dirt? No shine, no shape, nothing that looks like it could survive a rocket launch or live inside a human body for decades. But that's exactly the secret hiding inside this rock. Stick with me, because by the end of this, you'll never look at a titanium ring the same way again. I'm your host, and this is The Story Behind It, the show that cracks open the hidden origin stories of the materials quietly running our world. Before we go further, if you love uncovering how everyday objects are actually made, hit subscribe now so you don't miss what's coming next. Here's the strange part. Titanium doesn't come out of the ground looking like a metal at all. Unlike gold or copper, which can be found in nuggets and veins, titanium hides itself inside ordinary-looking minerals, mainly ilmenite and rutile. Plentiful, yes, but trapped. To break it free, mining crews turn to a brutal method: open-pit mining. Massive machines peel back layer after layer of earth just to reach the ore underneath. Australia, South Africa, and Canada lead this charge, hauling millions of tons of raw material out of the ground every single year. But pulling the ore out is only step one. Next, it gets crushed and rinsed, a process that strips away sand, clay, and debris, isolating the titanium-rich minerals from everything that doesn't belong. It looks almost too simple for something that ends up in spacecraft. But this humble first step is the foundation for everything that follows. And here's a twist you might not expect. Titanium isn't rare at all. It's actually the 9th most abundant element in the entire crust of our planet. More common than copper, more common than zinc, even more common than lead. So why don't we see raw titanium lying around everywhere? Because it's clingy. It bonds fiercely with oxygen and refuses to exist alone in nature, which means scientists have to force it apart from its chemical partners, a fight that takes serious heat, serious chemistry, and serious patience. That fight has a name: the Kroll process, engineered by metallurgist William J. Kroll back in the 1940s. Before his discovery, titanium was basically a lab curiosity, fascinating, but useless at scale. Here's how his method works. The ore gets mixed with chlorine gas and a carbon source, like petroleum coke, then blasted with heat near 1000 degrees Celsius inside a reactor. At that temperature, the chlorine rips the titanium away from its natural bonds, forming a new substance, titanium tetrachloride, a volatile liquid. Meanwhile, unwanted metals like iron get left behind as solid leftovers, filtered out of the equation entirely. That titanium tetrachloride still isn't ready, though. It has to go through distillation, a purification stage that strips out any lingering impurities, until what's left is a highly reactive, nearly pure liquid, primed for its next transformation. Now comes the moment where things actually start looking like metal. Engineers react that purified liquid with magnesium, sometimes sodium, inside a vacuum, completely sealed off from oxygen. This reaction tears away the chlorine entirely, leaving behind something new: titanium sponge, and the leftover magnesium chloride or sodium chloride. It doesn't go to waste. It gets recycled back into the system. But don't picture something sleek yet. Titanium sponge looks fragile, porous, crumbly, almost like a crystallized honeycomb. It's technically pure titanium, but it's nowhere close to the metal we recognize. There's still a long road ahead. If this kind of deep dive into hidden industrial processes is your thing, The Story Behind It puts out episodes just like this one, so subscribing means you'll catch every future breakdown the moment it drops. To turn that fragile sponge into something usable, it has to be melted down using serious industrial firepower. Two techniques dominate here: vacuum arc remelting and electron beam melting. Both work the same basic way. The sponge gets melted inside carefully sealed furnaces, where a vacuum keeps oxygen and nitrogen from contaminating the metal as it liquefies. This is also the stage where engineers often blend in other elements: aluminum, vanadium, tailoring the metal's properties to match whatever job it's headed for. Once melted and mixed, the molten titanium gets poured into molds, cooling into massive blocks called ingots. Those ingots are the true starting point for almost every titanium product you'll ever encounter. From here, factories reheat and reshape them into sheets, rods, tubes, even delicate wire, using enormous industrial presses and rollers to force the raw block into precise, usable forms. Slowly, this rock-turned-liquid-turned block becomes the backbone of aircraft, spacecraft, medical hardware, and high-end consumer goods. Here's the thing though. Plain titanium is impressive on its own. Strong. Lightweight. Naturally resistant to corrosion. But alloying it with other elements is where it becomes almost unbeatable. Take titanium, aluminum, vanadium, one of the most widely used blends in aerospace. Engineers love it because it delivers serious strength without adding serious weight, and it holds up under the punishing conditions of high-altitude flight. That versatility doesn't stop at airplanes either. You'll find titanium alloys in race cars, high-performance sporting gear, and even architectural structures built to survive decades of weather exposure. And then there's medicine, arguably titanium's most personal application. Hip replacements, knee joints, dental implants, bone plates. Titanium's rare gift is that it doesn't just resist corrosion inside the human body, it actually bonds with living bone tissue. That's not a small thing. That's the difference between an implant that fails and one that lasts a lifetime. Once titanium's been shaped into rough parts, it still isn't finished. It has to be machined, and this is notoriously brutal work. Titanium's hardness and heat resistance chew through standard cutting tools fast, which means manufacturers need specialized equipment just to drill, cut, or shape it with any accuracy. After machining comes finishing, and this is where the purpose of the part changes everything. Medical implants get polished to a mirror shine, ensuring a smooth surface that integrates safely inside the human body. Aerospace components, meanwhile, often undergo heat treatments designed to help them survive extreme stress and blistering temperatures at altitude. But none of this comes free. Mining scars landscapes and burns through energy. The Kroll process itself demands intense heat and generates waste byproducts along the way. Titanium production, in other words, has a real environmental price tag. The silver lining? Titanium is remarkably durable and recyclable. Aircraft components, medical parts, industrial equipment, much of it can be reclaimed and reused, stretching its lifespan and easing the pressure on fresh mining operations. And on the horizon, researchers are chasing something even better. The FFC Cambridge process, which uses electrolysis to pull titanium directly from ore in a single step. It hasn't replaced the Kroll process worldwide just yet, but it hints at a future where producing this metal doesn't have to cost the planet so much. So why go through all of this? The mining, the chemistry, the melting, the machining, just to make one metal. Because nothing else quite matches it. Few materials are this strong while staying this light. Few metals shrug off corrosion this well, or endure heat that would cripple steel and aluminum outright. That combination is exactly why titanium shows up in the places where failure isn't an option. Aircraft, rockets, submarines, and the human body itself. And it's not just functional, it's beautiful. Its natural silver-gray finish, and its ability to shift into vivid colors when treated, has made it a favorite among jewelers, artists, and designers, chasing something both strong and striking. From buried mineral to surgical implant, from raw ore to aerospace-grade alloy, titanium's journey is really a story about human persistence, about refusing to accept impossible and engineering a way through it instead. So next time you spot a titanium watch, a surgical implant, or a plane cutting through the sky above you, remember the road that metal traveled to get there. If this kind of story pulled you in, that's exactly what we do here every episode. Hit subscribe, ring the bell, and join us next time on The Story Behind It.